Yes, Muhammad.
Doctor, can you repeat the last slide, the free body diagram for mass 1? Can you repeat it? Only
You
mass
mean
1.
you mean the
Slide
example?
33. Yes, slide 33.
Okay, we will discuss it fully today, just to make sure everyone understands it. Okay.
Come.
Okay, so today is a continuation of modeling mechanical systems. The content for the next homework will be on that, so I will assign it on Wednesday, inshallah. So really the main idea is that you have, let's say, a bunch of masses, okay? And for every mass, you need a free body diagram. Then you use the element laws to express the relationships. And in the end, you will have a system. You will have a differential equation describing the system. So there are forces that correspond to the displacement. For example, the inertial force. Notice here that it is it corresponds to it relates to the acceleration of the system. You have forces that correspond to the displacement. You have here delta x. X is the displacement. So this is from the force due to spring for stiffness. You also have forces that relate to the velocity. So you need something that relates to velocity. You need something that relates to displacement, and you need something that relates to the acceleration. And this is a damper. So then we had interconnection laws, and we focused on D'Alembert's law, which is a restatement of Newton's second law. So instead of saying the sum of external forces is equal to the mass multiplied by the acceleration, we just put this to the other side, and that's pretty much it. If I have an applied force, then it will come in here. I had a few examples last time, and today let's explore the example where we stopped last time. Also, we mentioned something about serial and parallel combinations. For serial combinations, it's like parallel resistance and electricity systems. And also for parallel combinations, here we have summation. It's like serial resistance in electric circuits. We have this example. This is the example we stopped at last time, right?
Yes.
Okay. So we have two free body diagrams here because we have two masses. So I have mass 1 and I also have mass 2. So every body diagram needs to be balanced in terms of forces. So I can plot the forces to the right and the forces to the left. So for example, here I have a force due to this spring, this one, right? So it is what? It is K1 x1. Then I also have the inertial force. So the movement is to the right, right? This is the reference direction. Because the reference direction is to the right, the inertial force will act in the opposite direction. So this is m1 x1 double dot. Now what are the forces to the right? So I don't have a direct applied force like in mass 2. So the force will come from here through the spring and the dashpot here. So we have force from the spring, K2 x2 minus x1. We have another force from the dashpot, which is B x2 dot minus x1. dot. Is that clear for mass 1? Any questions about that? Yes, Muhammad.
Doctor, why for K2 we have x2 minus x1 وعند x1 بس واحدة يعني
Okay.
باليمين واليسار.
Okay, so K2 is between two masses, right? And each one of them is moving according to a certain displacement. So it is affecting the two masses. So we take the relative displacement. The spring is usually connecting two bodies, so it affects both of them. So the way it shrinks, or let's say its length changes, that is affected by the two masses and the two displacements. So this is in a sense the displacement of the spring. For K1, it is only connected to the first mass. So the only displacement that is affected by it is just x1. For K2, it's different because you have two displacements being affected. So you take the relative displacement, the difference between the two. The one, let's say, so the one that is further direction, the reference direction minus the other. If I go back to the element laws, you can see that so here it's kx, right? It's like x minus 0. There is no other displacement on the other side. This is the reference position, it is 0. So we just skip that 0. Now if I go to this one, so we had an example before that. See, it's kx2 minus x1 because its length is changing according to the difference between the two displacements.
Yeah, clear, thank you.
No problem. Okay. Now for mass 2, what do we have? Again, we have, yes, Abdulillah.
دكتور معليش بس انا ما اقدر احدد x1 و x2 يعني ما اعرف وش هي اكزاكتلي يعني لو كانت الدايجرام هذا اللي قدامي كان فيه كل اطوال كذا فوق الام 1 في طول وجنبه يمين وكذا يسار وفي اطوال ما راح افرق اي واحد فيهم x1 و x2 لاني ماني فاهمها اكزاكتلي يعني ما ادري ايش تمثل x1 و x2.
Okay, but x1 is the displacement of m1, x2 is the displacement for m2. Okay, so here you are not trying to.
يعني معليش M1 كان قبل يعني في اليسار وهذا بعد ما صارت عليه الابلايد فورس لف لين اليمين.
Yes.
Displacement from the original plate to the new place.
Yes, this is where it starts. Correct. You have an applied force.
Thank you.
No problem. Also here you're building the relationships between the variables. Now how to solve it is another story that we will discuss later. But here we're just building the model. Okay? So for mass 2, you have an applied force here, F of A. Do I have anything on the right? Anybody wants to add another force to the right? Abdulillah, do you still have something to add?
لا كل شيء تمام. يعطيك العافية دكتور.
Okay. So there is no other forces to the right of mass 2, but we have forces to the left of it. We have a force due to the spring. It's the same, K2x2 minus 1, but now it's acting the opposite direction. Similarly for this force, Bx1 dot minus x2 dot minus x1 dot. And we also have a third force here, which is the inertial force. This is m2 x2 double dot. Now we drew the free body diagrams, and we have the forces and all the directions. We write the equations. So we have one equation for every mass. So for mass 1, what we have is just this, right? We have k1 x1 plus k2 x1 minus x2. Notice something here. It was x2 minus x1 to the right. Now I lift it to the left. So I'm putting all the forces to the left. Using D'Alembert's law, we sum all forces and they're equal to 0. If there is no applied force, if there is an applied force, then you put it on the other side. It's really up to you how you want to put forces in every side. However, you will see later in control in our standard notation and standard way of doing the analysis. This will make the analysis easier later on. Then we have also b x1 dot minus x2 dot. This is also we have plus m1 x1 double dot. All of this is equal to 0. Okay, can somebody tell me the equation for the second body? Yes, Yasser, please go ahead.
Doctor, firstly, why you didn't put a negative sign for k2 multiplied by x2 minus x1 and b multiplied by x2 bar dot minus x1 dot?
I actually did, but the thing is I flipped it. I made it x1 minus x2.
Ah, I see.
Yeah.
For the second mass, we will have k2 multiplied by x2 minus x1.
Let me use another color. K2 x2 minus x1.
Plus
Yes.
b
Plus b.
multiplied by x2 dot minus x1 dot. Plus m2 x2 double dot.
Yes.
Equal the applied force.
Exactly. So now we have two equations, two differential equations, describing the entire dynamics of the system. So remember, x1 dot, x1 double dot, and similarly for x2. These are all functions of time. We're actually studying how the system behaves in time. So if I put an applied force of 5, and I know, let's say, the mass and the coefficients, then if I can solve these differential equations, I will know that the displacements exactly. And as you can imagine, dealing with these differential equations can be sometimes complex. So we will introduce new techniques. We will introduce what's called the Laplace transform, so that we transform these equations into something easier to solve using just math 001. Did we forget inertial force? No, we didn't. It's actually this one and this one. This is the inertial force. Great. Any questions about this example? Okay. If you don't have a question, then let me move to the next one. Okay, please grab a piece of paper on your own. Work in this example. So first you need to do the free body diagram. I'll just use diagram. Then identify the forces. Then you will have one equation because you have one mass. So find the ODE, the ordinary differential equation. How much time do you think you need for this example? Maybe 5 minutes? Okay, so let's give it 5 minutes, and then we can solve it together. Yes, Yasser.
Doctor, in this example, is the applied force the same as the gravity force?
No, it's not. Applied force is something you apply to the system.
Okay.
Yes? Did he have a question, Abdulillah?
Yes, doctor. About the gravity force, do we put G or acceleration? Doesn't
Okay.
make any difference, right?
Okay, so it's okay. It's not the same as MA, the
X,
MX double dot. It's not the same as that.
it's mg, right?
MG, yes.
Oh,
Yes,
okay, thank you.
Mhm. Have you solved it?
I finished.
Yes. Can you please
Yes.
tell us what you have?
Okay. We have two forces to down, okay, which are the gravity and the upright force. And for above باتجاه المعاكس لها we have the spring and B and also the inertia.
So we have, what is the force due to the spring? Kx.
Vx and also we have Fi and Fb. Okay, Px and
Dot.
Ma.
And we have
Ma.
m
Double X.
x double dot. Okay, good. So let me write this equation and discuss something. Is it clear for everybody what we just did? Please, if something is not clear, just stop me at any time. Okay, so if we write everything, so we have m x double dot plus bx dot plus kx equal to f of a plus mg. So usually for differential equations, you have, let's say, an equilibrium position. Okay, so let's say that I have an equilibrium position x naught. Okay, this is the starting point of the system, and I want to measure the effect of this extra force on that x naught. So if I have x naught, then I have x naught dot is equal to x naught double dot is equal to 0. Why? Because it's a fixed point, it's a constant, it's a certain number, so its derivative is 0. And this is aligned with this ODE, right? So if I do that, then we get the following. We get kx dot is equal to mg. Why? Because at the equilibrium position, you have the three things. You have these are being equal to 0, and also you have no external force, so it is 0. So the equilibrium position is the position at which you start the differential equation. So you have a differential equation, you want to find the solution according to a certain initial condition, and you want to study the effect of the force. So at the initial condition, you have no external force, Fa, and you also have no, let's say, velocity or acceleration. So if I have this equality, okay, and define a new variable, call it z, z is equal to what? It is, or maybe let me write it in another way, just, yeah. Yeah. So we have, what is the position x here? X here is really the initial position, x naught, plus certain displacement z. This is, so if I want to split the displacement of the mass x into two parts, the equilibrium position plus the position due to the force. So call it z, x naught plus z. And again, apply it here. What do I get? We have m. Again, this is 0, x naught double dot plus z plus b x naught dot plus, sorry, this is z double dot, z dot plus, again, k x naught plus z is equal to what? F of a plus mg. Notice the following. This is 0, This is 0. Okay. So what do I get? I get mz double prime plus bz dot. So I use prime and dot alternative. I use them interchangeably. Okay. Plus k x naught plus z is equal to what? F of a plus mg. Notice something here. We had this equality, right? That basically the force due to the spring at the equilibrium position is the same as the gravitational force. So I can cancel these two, and we get bz dot double dot that bz dot plus mz double dot plus kz is equal to f of a. Notice what happened here. We can ignore the effect of the gravitational force if we're only interested to see how does the system behave due to an external force f of a or applied force f of a. So using this derivation, I just showed you that this equation is actually equivalent to this if you're only interested into the effect of the applied force. So when you draw the free body diagram, and when you write the system equation, you can ignore the gravitational force if you only consider the displacement due to the applied force f of a. And this is what we care about. We care about how will your force, the additional force, the applied one, it change the system behavior. So you can just ignore the gravitational force. Is this clear? Yes, Faisal.
Doctor, this is only true if we have at least one spring and the body is positioned vertically, right?
Yes.
Okay.
If you are at equilibrium, then you are not moving, right? And if you have a vertical body at equilibrium that is not moving, it means there is something that cancels the gravitational force. So if you don't have a spring and if you don't have anything that cancels that, then how can it be in equilibrium? Then it's a moving target, it's a moving object, it's not at equilibrium. The equilibrium is just a fixed position. So naturally, you need a spring or something that can offset the gravitational force if you are at equilibrium. Usually, we take the equilibrium to be 0 and then start from there. But I just wanted to elaborate at this point. Of course, this is for linear dynamics. If you go non-linear, then it can get complicated, but it's not something we're addressing in this course. Any questions about that? Please, if you have any questions, let me know. I think this is an important example. Okay, in case there's no questions, let me clear all this. Yeah, I had a question here just to indicate the importance of that, but I got excited and just kept explaining it before we see it in the slides. Okay. So I have 2 more examples to study in this lecture. So let's start by, so basically, I mean, these examples are just to show you different variations of dealing with these free body diagrams, but these are not comprehensive. I think you need to practice different cases, different scenarios in order to get comfortable. And also in the homework, you will see new examples too. So now, suppose we have these two bodies, M2 and M1. So let us go through this one. So let me plot the free body diagram for M2. Okay. Is this color clear, or do you want me to use a darker one? Because it seems light.
Yeah, darker, please.
Okay. So let me use black. So we have M2, right? Let me put M1 here down below. So for every mass, we have an equation. So let's plot the forces, and then let's draw the forces, and then we can talk about the equations. Okay, so what are the forces to the right of M2? We have Fa, the applied force. Anything else to the right of M2? No. Okay. What are the forces to the left of M2? Yes, Abdelina.
Doctor, can we consider them as a one object?
Are they one object? They are not one object. I mean, if they are, let's say, if they have the same displacement, the same applied forces, the same everything, then yeah, but these are not one. I mean, you can still make a one object and find a free body diagram for that one object, but I think that will not be a comprehensive case, right?
Okay. Thank you.
No problem. Okay. So this is M2. Okay, give me a force to, so let me ask you a question and you can tell me the force. So what is the inertial force on M2? Yeah, what is it? Can you give me the expression for it? Is it K2x plus z? Is this the inertial force? It is M2 x double dot plus z double dot. Why is that? Why do I have a z here? Why isn't it just z? Why do I have an x? Why is this not just z?
Doctor, because it's more than x, more than m1 by z.
Okay, so if I have something like this, is it z or x or what? If this is a reference position.
Just Z then.
Correct. So please be careful about how these references appear. Dependent on the reference position, you might have different equations describing the system. Okay? All right.
دكتور
Yes.
الحين يعني الفرق يعني بين الريفرنس واللي مو ريفرنس الشخوط هذه اللي على جنب.
أيوة, yes. We represent the reference position by these lines. Correct.
اوكي.
Okay? It's mentioned in the slides in the beginning. We use that to denote the reference position. Okay, so we have the inertial force to the left. We also have a force due to the spring. What is that force? It is K2 what? K2 x plus z, right?
No.
Why not?
Why is he? Sorry for M2 this one. Yes, sorry. By
This
M1.
is for M2. Yes, this is M2.
Yeah, sorry.
Okay. So we have a force due to the spring. We have an inertial force. We have an applied force. Do we have other forces?
Yes, doctor, we have the friction force.
Okay, I'll plot it here to the right and with an arrow to the left. What is that friction force?
It will be B2 multiplied by x dot plus z dot.
B2 multiplied by x dot plus z dot. Is it?
Doctor, I believe it's only Z.
We have B2 z dot. So why is that?
Because the friction is only between M1 and M2.
Okay.
So it didn't start from X.
Exactly. So there are forces which we study in terms of the relative motion or the relative displacement, and there are forces which we study in terms of the absolute elongation. For example, for the inertial force, we go until we hit the reference position. For the spring, the reason we had it x plus z is because it's actually, covering these two distances. But for the dash part or the friction, actually for the friction, sorry, it is only proportional to the relative displacement, so that it's just B2 z dot. We do not have x added to it. It's just B2 z dot. Is that clear? This is 2. Okay. So let me deal with mass 1, and let me use a bigger, free body diagram. So this is mass 1. Okay. So can you identify a force to the right? Okay, FK1, K1x, is it to the right? Is it acting, is it helping mass 1 move further to the right, or is it making him move slower to the right? If it's helping it, then it's to the right, K1. So Faisal, what is FB2? What do you mean by FB2?
Since we have an applied force to the right, so the second mass or M2 is dragging M1 to the right. So it will be a friction to the right. So the friction force is acting, or actually it's dragging M1 to the right. So the only applied force to the right will be B2.
Okay, so yes. So we have B2 Z dot, right? So in order to identify the direction of a force, you need to see, does it help the body move or the mass move to the reference direction, or does it oppose to that movement? If it helps, then it means it's a force to the right. If it doesn't, then it means it's a force to the left. In this case, for mass 1, this is really the only force in which it can move. Now, for the forces to the left, we have K1. K1 what? Is it X or Z? Or X plus Z? X plus Z, Yasser. Why? Faisal is saying it's only X. So why is it? Okay. So let's hear an opinion saying it's X plus Z, and let's hear another opinion saying it's just X. Can somebody who thinks it's X plus Z tell me why? Okay, why is it just X? Why do I ignore Z here in this case? Yes, Muhammad.
دكتور M2 ويعني هي اللي كانت تتحرك يعني معاها الزي لأنه كان relative to M1. بس M1 تتعامل بس مع الإكس مباشرة يعني فما أظن إنه له علاقة بزد.
Exactly. Excellent point. Yes, that is actually correct.
بس دكتور عندي سؤال الحين ليه مو مقتنع بسالفة البي 2 زد دوت حقت الام 1 هي تأثر على اللي فوق ليش ما أتوقع إنه يتساهم على ام 1.
Okay, B2 is connected to just M2 or M2 and M1.
مرة ثانية.
Where is okay? Is B2 affecting just M2 or M2 plus M1?
both بس أحس تأثير على ام 2 بس ما أحس إنه تأثر كثير على ام 1.
Maybe. I mean, so if you solve, I mean, you cannot. Okay.
لو حرك صندوقين فوق بعض وأدف اللي فوق ما أتوقع اللي تحت بيتأثر كثير.
But it can still move even if it's very minimal, right?
ممكن.
And it can still be affected. So it's the only force that might help. I mean, maybe if you solve it, you get 0.001, but it's still a force that we can't ignore. We plot all forces that we see, and that force exists. Okay. And the way it exists is that it affects M1, and the way it affects M1 is that it helps it move to the reference direction, maybe minimally, but it still does. So we cannot ignore it. If you put your hand on a piece of paper and move your hand, that piece of paper will move due to friction, right?
Yes.
So yeah, so it's still a force.
Okay, thank you.
No problem. Maybe you need M2 to be much bigger than M1 in order for you to see that, you observe that behavior, but it is still there. Okay. Then we have a force due to this dash part, right? B1. So we have B1 X dot. We also have a force due to this friction, B3 X dot. Finally, we have the inertial force. What is the inertial force here? M1 what? It is M1 X double dot. Okay? Now, can you get two equations describing the system dynamics using these free body diagrams and the forces we just identified? Yes, easily, right? So using D'Alembert's law, we will rearrange the forces here such that all of the forces, some let's say call it Fk, or maybe K is a bad notation here, so let me use something else, call it Fn or Fi small I, as in the beginning is equal to 0. Here, the summation of the other forces, some forces Fn is equal to F of A. Maybe let me just change the handwriting here a bit. Maybe let's just use I again. Okay, using D'Alembert's law. So Fi's here are just what? It's this guy plus this guy plus this guy plus this guy, then minus this guy. Fi here is what? I have force due to spring, the inertial force, the force due to the dashpot, or the friction, being equal to the applied force. These are two equations describing the system dynamics and describe how all of these variables that are functions of time behave. Okay, and if I give it an applied force, and if I know the parameters of the system, the coefficients and the masses, then I can know exactly for every mass what is its displacement, is the corresponding velocity and acceleration. Now, is this clear what we just did? Yes, Mazen.
دكتور معلش بس بالنسبة للانيرشال فورس الام 2 مو المفروض تكون اكس بلس زد الكل دبل برايم؟
M2, yes, this is what happened. Okay, yeah, but I mean, the thing is, if you, let's say, x plus z all double prime is simply x double prime plus z double prime.
اوكي.
This is from the properties of the derivatives. Any other questions or comments? Okay, let me take a quick poll here. Clear? Please respond to the poll. I just want to know how clear this is. Yes, Abdurrahman.
Doctor, regarding the friction on M2, it's always opposite to the applied force, right?
You can say that, but imagine if there is a third mass on top of M2. So always ask yourself, does this friction act in the opposite direction or not? Usually it does, but sometimes you have some cases like this one in which it is moving in the direction of M1. So this is how you know, does it help it move in the direction or not? And yes, friction is typically an opposing force.
Okay, thank you.
No problem. Yes, Abdurrahman. Abdullah?
Doctor, why is the friction on M1 going to the left?
B3 and B1 are both influencing it to the left, right? B2 is to the right.
Yeah,
Which
but it's the only force going to the right.
Yeah, but we have different frictions. We have a friction here, and we have, let's say, I mean, this is, let's say, due to the dashpot. So B2 is the one to the right, B3 will act to the left, and this one will act to the left. So this is B2 to the right. We have multiple frictions. Do you see that?
Yeah.
Yeah. Is it clear?
Not entirely.
Okay, what's not clear? Which one is confusing you?
It's just confused me because usually when we look at the friction, we have Fa to look at the applied force, but here there aren't any specific applied force to indicate where the friction is going to be, because it's usually the opposite of the applied force.
Yes, it is the opposite for mass 2. However, for mass 1, this is the only force that might move it to the right. Imagine if you put your hand on a piece of paper and move your hand. Will that paper move in the direction of your hand?
Okay, now I understand now.
Yeah. Okay. So, yes, Abdullah.
دكتور ليش K1 X لليسار ليه مو لليمين يعني؟
K1X, okay. Does this spring help M1 move to the right? Or does it actually push it, make it harder for M1 to move to the right?
اوكي يعني البي قاعد يسوي له بوش لليمين.
B2.
اوكي ثانك يو.
Okay. Abdullah Sheikh, do you still have something to add? Okay. All right. So now, let me erase everything and tell you that if we add another reference position here, these equations that we just derived will actually be different. So if you look at the handout, you will see there is a discussion on this point, and there is also other exams that you can study, and then that will prepare you for the next homework, and hopefully after the homework you will be well prepared for the tests and also the learning outcomes of this class. So let's explore another idea. And let's say that we have an ideal poly. So this has no force whatsoever. So we just ignore all the forces that correspond to this poly. And we have the two bodies here. So if I want to find the force due to, first of all, do you want to try it on your own for maybe 5 minutes before we discuss it? Or do you want to, okay, have 5 minutes, try to solve it, and then we can chat about it. Okay, have you solved it?
Yes, I tried.
All right, what do you have?
For M1, we have applied force to the left,
Okay.
and against it, الثانية, we have for the spring, force of spring and the friction.
So we have f of a, we have k1. What is the force due to the spring?
K x1, x1.
x1 minus x2. Okay, the
ليه
spring is connected
تسمع
to
الرقم الثاني بعد؟
the spring is
okay.
connected to both,
Yes, I see.
right?
X, minus X.
We also have the b1. This is x1 dot, so because it's not connected to any other. Yes, Abdullah.
Doctor, didn't M1 move to the left?
It moves to the left due to Fa, but you still have a resistive force, which is the spring.
Oh yeah, okay. I just understood it.
Yeah.
Misunderstood it.
Yeah.
And for M2, I think Dr. for M2, it's moving up a little bit. So we can't
Done
compare.
with M1?
We
Yeah.
say, okay, it's FA.
I see what you mean, but let's first finish F1, M1. Are we done with M1?
I think so.
Don't we have an inertial force on M1?
مو هي B1?
Inertial force.
B1 وش وجه؟
B1 is due to the friction.
Yes. Yes,
I'll put it
then
because
we have it, yes.
it's
Yeah,
always
forget about it.
forgotten. So I'll put it like this.
Mm-hmm.
Now it's complete. So we have this guy plus this guy plus this guy being equal to Fa. Dallenberg's law. Yes, Mazen.
مو المفروض الفورس حق الام 2 الويت حق ام 2
المفروض what?
we add the force of the weight of M2 M2G.
Yes,
As
so
a
this is okay. The force on what exactly?
as a force acting on M1 pushing into the right side.
Okay, so again, you check the forces that are directly connected, directly affecting M1. Now, if there is a force that is affecting M2 and it's also affecting M1, it will appear somehow. Remember, this force K1 x1 minus x2 is actually a function of both displacements x2 and x1, and displacement of x2 is the displacement of m2. So m2 will appear instantly. And remember, this is just the free body diagram for the first mass m1. We still have another free body diagram for m2, and the system is described by two equations, and these two equations will have everything. Okay, so you look at the forces that are directly affecting the mass. This is the beauty of it, actually. And then if there is something that is indirectly affecting it, or M2 will appear, but it will not appear directly, you can still, after you study the system of equations, it will influence you, but not directly. You do not just use M2 and M1 directly. Does this answer the question?
Yeah, it's clear now.
Okay. So for M2, what is the force that pushes it to the top?
Also, if applied.
No, if applied is applied directly on M1. It's not directly applied to
Yeah,
M2.
but it helps the friction, helps the spring getting up.
Yes, so it's the spring, the force due to the spring, which is also influenced by the applied force.
No, yes, هذا قصدي.
Yeah, so x1 minus x2. Okay, any other force to the top?
دكتور متى نقول x2 minus x1؟
Okay, you look at the reference directions.
Mm-hmm.
And you will see, let's say here you have two displacements, x2 and x1. You take the x1 minus x2 because x1 is the one further to the left. Why? Because and also it's the one further in the direction of the in the reference direction. The reference direction here is to the left. So x1 is the one further to the left, so we take x1 minus x2. Okay?
For both of them, for M1 and M2.
Yeah, I mean, if you, yeah, we take it the same in terms of magnitude, and then vary the direction.
Okay, clear. Thank you.
Yeah, in one of the earlier slides, in this slide set, you will see that we usually take it like that. Because if you have a spring and if you pull it from the left, right? Let's say the reference direction. And x1, you will have x1 minus x2. This is the distance it will extend at. Okay? With some practice, it will be clearer. So, but the thing that to care about is really the reference positions and the reference direction and the relative displacement. Okay. So for M2, we have two obvious forces. I'll write it down here, which is K2, X2. Another obvious force is B2, X2 dot. Now we have two more forces. One of them is the inertial force. I'll put it in red because people forget it. I'm the first one to forget it. So M2, X2 double dot. And we have also another force. What is that force? mg, correct. So we have m2g. So let me plot it here. m2g.
Dr. Constant displacement as in the previous example, or
Here we don't. I mean, because you're connecting it to two. Let me see how to answer this question. This is a good question. You may ignore it if you assume a certain, let's say, if the motion is vertical, and it is vertical motion reference to F2. So if X2 here, if you're only concerned about the force due to the displacement due to the applied force and in the beginning, then yeah, you may ignore it. You may ignore the gravitational force. However, I typically don't ignore it. The reason I showed you how to ignore it, or why it's okay to ignore it, is just to elaborate on the issue of having okay, you have a fixed position in the beginning, and then you want to study the influence of the applied force only. But here
okay.
we're looking at the total force, so we don't ignore it because we don't have a reference equilibrium position that we're comparing to yet. But maybe if we try to solve it and you have a reference position, you can do that with those kinds of manipulations.
Okay. Sounds clear.
Does that make sense?
Yeah.
Okay. Is it clear, everybody? Yes, Abdurrahman.
Doctor, when we ignore the gravitational force, do we have to have like another force to cancel with?
Okay, so the gravitational force is usually offset by another force at the equilibrium position. So you can ignore it when you only consider the force due to the additional, let's say the applied force that you impose in the system. So in this case, I can ignore let's say the gravitational force if I consider a new variable, call it, let's say, Z2, and then do something similar to what I just did in the previous example, and then adjust the equations accordingly. I need to adjust them accordingly, then yes, we can do that. For example, x2 will be Z2 plus x2 naught, some equilibrium position, and here in this case, I will have the same, and then I will have, let's say, so here M2 will be M2 Z double prime, and also Mg will be ignored. But when you ignore it again, the corresponding displacement, velocity, and acceleration for that mass need to be appropriately changed so that you don't mess up with the system. So you need to have, let's say, an initial displacement, initial position, and that initial position is where you start the analysis. So yes, to answer your question, yes, you need something to offset the gravitational force. Otherwise, if you don't have that, you don't have an equilibrium position. The system will keep moving, so it will not. So in the beginning, it was not at equilibrium. The equilibrium meaning is that you have a constant displacement, meaning that it's not moving. Does this answer your question?
Yes, clear. Thanks.
No problem. Okay. I encourage you to go to see example. Let me see which one here. I mean, first of all, please go through the handouts. And also there is an example here that you can go through. I think it will be a good exercise. Example 2.6 from the handout. Okay, these examples that we solved in the lecture are not comprehensive. They're just intended to really give you a flavor of the things we cover in this section of the course. So please study on your own, read the handout, and try to explore different examples.